We continue working on problems from Seagal's biochemical calculations. We are in page 93, and this time we are going to work on problem number 50. Again, that's in page 93. This problem asks us to describe the preparation of 1 liter of a 0.2 molar solution, 0.2 molar histidine buffer, and also with the pH equals 6.5. pH equals 6.5. Then it tells us that we have to start from a solid histidine hydrochloride monohydrate. So we are going to have histidine hydrochloride monohydrate. So that's the material available to us as a source of histidine. And it tells us that this salt, the molecular weight for the salt is 209.6, which is information that we don't need, but it's nice that's provided. And also it tells us that we have at our disposal 1 molar solution of potassium hydroxide for us to adjust the pH. And it tells us that the pKa the pKa of the side chain for histidine is 6.0. And additionally, it tells us that the histidine hydrochloride is the same as the amino acid with 1 charge AA+. So we have that information, and let's see how we approach this problem. First of all, is always to our advantage to write the structures of the forms of the amino acid, so you know exactly where we are in terms of the solution that we have in mind. So we start with the fully protonated form of histidine, which is NH3+, CH, COOH, again fully protonated, right? CH2, and then C, N, the bond C, put hydrogen, and hydrogen. And remember that this is the side chain, and that's the one that has a proton that can be deprotonated. So you have 3 places here we have protons that can be deprotonated, and we know that the first step is going to be deprotonation of the carboxylic group, the proton from the carboxylic group, because that's the lowest pKa, right? So first step, this is going to go to H3Na+, CH, COO minus now, because it's going to be deprotonated, CH2, C, double bond C, N, double bond C, N, H, 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 and H. This remains protonated, right? So now we start first with histidine 2+, or +2. We have 2 charges, right? We have 2 charges for histidine, one here, another there. So that's 2+. This one here, we have a positive charge here, negative charge there. And then we have, so the overall charge of this form of histidine is histidine plus. So this is the one that we are working, right? But this, when you put in water, still keep going on, especially with when we titrate with sodium hydroxide. And the next step is going to be deprotonate the side chain of histidine, because the amino group has a higher pKa, right? So this amino group here remains protonated, CH, COO minus, and CH2, see the bond C, N, C, so H, H, H. Now we don't have any protons in here, okay, because it was deprotonated, and now this thing has a positive charge here, negative charge there, so this is going to be his 0. For our problem, we don't need to go on and go to the next step, would be to generate histidine -1 when we deprotonated this proton here from the side chain, because the pKa was going to be so high that's not relevant for our solution. So we have here the pKa1, the pKa2. Now we have identified the buffer that we are going to be working, because if this pKa is 6 and the pH that we want is 6.5, we are going to have these two forms of histidine plus and the histidine 0. In other words, our problem is a buffer where the acid is histidine plus in equilibrium with histidine 0 plus a proton. So how we determine the concentration of these two species, the buffer and the conjugate the base? So the way to determine that is to use the Henderson-Hausberg equation. So let's do that. Let's move the next page here, and let's use the Henderson-Hausberg equation for that. So here we had the histidine in equilibrium, histidine 0. So now we have for the Henderson-Hausberg equation is going to be pH equals pKa2, because we already identified the step is step 2, plus log of the concentration of, in this case in here, histidine 0 divided by the concentration of histidine plus. Remember here, in this particular equilibrium, histidine 0 is the conjugate base, right? So now from this we can calculate the pH, the ratio of these two species, because we know the pH, we know the pKa. So let's do that. Let's plug in the numbers. We have here pH that we want, 6.5. We have the pKa that we know that was given to us. And then we have the log of the concentration of his 0 over the concentration of his plus. From that, we can say that the concentration of his plus over the concentration of his 0, concentration of his 0 over the concentration of his plus is going to be 10 to the power of 6.5 minus 6. In other words, 10 to the power of 0.5. 10 to the power of 0.5, we have a calculator at our disposal here and the exams as well, so they give us 3.16. So we know now that this ratio here is 3.16 as dictated by the pH that we want for the solution. Therefore, we have one first equation here that tells us that his 0 equals 3.16 times the concentration of his plus, correct? And we have a second one. We know that the concentration of these two species together makes the concentration of the buffer what was given to us, 0.2 molar. So if you put this thing together here, so then another one that we have is that his 0 plus his plus is going to be equal 0.2 molar, or equals 200 millimolar. Now, this is his 0, this is his 0, so I know that his 0 is also equal 3.16 histidine, so I replace it there and they make it 3.16 his plus his plus from the equation here, and equals 200 millimolar. From that, I know that 4.16 times the concentration of histidine plus is going to be equals 200 millimolar. So therefore, the concentration of histidine plus is going to be 200 millimolar divided by 4.16, which gives us 48 millimolar. So the concentration of his plus equals 48 millimolar. All right. So if you have that, we know then that the concentration of his 0 is going to be equal 200 minus 48, no calculator needed here, 152 millimolar. All right. So the concentration of his 0 is 152 millimolar, or if you want to work in molar, you are going to get 0.152 molar. So what does it tell you is that in order for you to have this pH, you can put his plus, but you have to adjust the concentration from his plus to make it as much as 152 millimolar of his 0. And how do you go from his plus to his 0? By adding potassium hydroxide and the potassium hydroxide in the same amount. So let's calculate now what we need to do to adjust this concentration. Keep in mind that we wanted to have this concentration of his 0 at 0.152 molar. All right, so first let's calculate how much we need of all species of histidine combined. All species of histidine, all his forms, regardless whether it's going to be plus or zero, it's going to come from one source, and that source is histidine hydrochloride monohydrate. So we want from this one here, we want to make a solution that's 1 liter and the molarity is 0.2 molar. So this is high school chemistry now. We go back and calculate the molarity, good old days of high school, mass divided by molecular weight and the volume in liter, right? So from here, we have the molarity is going to be, the mass is going to, mass in grams, is going to be molarity times molecular weight times volume in liter. We have all these numbers. The molarity, the molecular weight was given to us. The molarity is 0.2. The molecular weight of this compound was given to us as 209.6. If not, we could calculate that. And the volume of the solution that one is 1 liter. So 0.2 times 209.6 give us 4192. Okay, so you pick up 4192 grams of his HCl monohydrate. So this is something that's available to you. Let's mark that in here. This is one of the things that we are going to add in that solution to get what you desire. All right, but now if you put this salt there into water, the concentration of his zero is not going to be the concentration that you want. Therefore, the pH is not going to be 6.5. So now let's adjust that. And to adjust that, we have to keep in mind that we need his zero to be 0.152 molar, 0.152 molar. All right, so we know that's 1 liter of solution. So the number of moles of his zero that we want is equal 0.152 moles. No, no big deal here. We just have 1 liter, so 0.152 mole, right? And how many moles of potassium hydroxide we need? The same, because the ratio is 1 to 1. Okay, so from that we know that the number of moles of potassium hydroxide that we need is 0.152 moles. I have a solution of potassium hydroxide, so I have to measure the volume to determine how much of that volume is going to deliver the 0.152 moles of potassium hydroxide that I need. Okay, so this is not a big deal again. We know from chemistry that molarity equals number of moles divided by volume in liter. Therefore, the volume in liter of potassium hydroxide that I need is going to be the number of moles divided by the molarity. So the volume of potassium hydroxide, KOH, in a solution 1 molar is going to be 0.152 divided by the molarity of the solution, which is 1, right? So it's going to be 0.152 liters of the solution of potassium hydroxide. Or, if you wanted to put in milliliter, 152 milliliters. So now we know what we want. What we want is, we want potassium hydroxide 152 milliliters. So now how you do this thing? We have to mix up this thing, and at the end of the day, you have to have 1 liter. So one thing that we don't do in the lab is to pick up the quantity of salt of the buffer that we need, like the his hydrochloride monohydrate, and then put sodium hydroxide on it. There's no point in doing that. What we do is that first we dissolve that salt and make a solution, and then we add the potassium hydroxide. So you have to be cognizant of the fact that at the end we want 1 liter. So pick up any volume that you want. 400 milliliters, 500 milliliters. Okay. Don't pick up 900, for example, because when you put 152 later, it's going to be more than 1,000, so you are in trouble. But let's say 600 milliliters of water, dissolve your salt there, this his hydrochloride monohydrate, dissolve well. Then we're going to add now 152 milliliters of potassium hydroxide, 1 molar. Then we adjust the volume with distilled water until it becomes exactly 1 liter. So we have now your solution, a histidine buffer with pH 6.5, which, by the way, is a very useful solution to have in the lab.